The Large Hadron Collider, LHC, at CERN is the world's largest and most powerful particle accelerator. It has just started its 2024 physics data collection season. Over its 14 years of operation, the LHC has tackled some of the universe's biggest mysteries by colliding countless particles at nearly the speed of light in a tunnel 328 feet underground. One fascinating aspect of the LHC is that scientists can't predict exactly what will happen when protons collide at such high speeds. Despite its groundbreaking work, by the end of its second run in 2018, the LHC had only collected about 3% of the data it is expected to gather over its lifetime. This means many discoveries are still to come. Scientists hope the LHC will help solve major mysteries in the universe. Recently, the LHC has produced extraordinary and puzzling results, hinting at breakthroughs that could revolutionize physics. Let's explore what makes the LHC so remarkable. The birth and operation of the LHC. The idea for the LHC dates back to 1977 when Sir John Adams, a former CERN director, proposed building an underground tunnel for a high-energy particle accelerator. The project was officially approved in 1997, and construction began on a ring that crosses the French-Swiss border. This ring accelerates particles to 99.99% of the speed of light, colliding them to produce energy and new particles. The LHC uses 9,300 magnets to guide charged particles in opposite directions at a rate of 11,245 times per second, creating around 600 million collisions per second. These collisions generate enormous amounts of energy, occasionally producing exotic, never-before-seen particles. Discoveries and upgrades. Since its first operation on September 10, 2008, the LHC has undergone several upgrades. After being turned off in 2018, it resumed operations on April 22, 2022, with higher power and double the collision rate. The goal is to reach record-breaking collision energies of 13.6 tera-electron volts. There were initial fears that the LHC might create Earth-destroying black holes, but reputable physicists, including CERN Director General Robert Amera, assured that these fears were unfounded. However, the LHC does have potential hazards if used improperly. Major experiments and the Higgs boson. The LHC has been instrumental in conducting two main experiments, ATLAS and CMS, which operate independently to ensure unbiased results. These experiments have produced over 2,000 scientific papers on fundamental particle physics. On July 4, 2012, researchers announced the discovery of the Higgs boson, a crucial part of the Standard Model of Physics, which explains how particles acquire mass. Despite this discovery, the Standard Model has limitations. It doesn't account for gravity, antimatter, dark matter, or dark energy. Scientists hope that the LHC might uncover new particles or forces that can fill these gaps. Current anomalies and future prospects. One intriguing anomaly was first noticed in 2014 when beauty quarks decayed into muons less frequently than into electrons, which is unexpected since muons and electrons are supposed to behave similarly. This suggests the possible existence of new particles affecting these decays. Recent results have strengthened this anomaly, reaching a confidence level of over 3 sigma, indicating a low probability that the result is a random fluke. The role of data and machine learning. The LHC generates a massive amount of data, about a petabyte per second, but only a small fraction is saved. This data is critical for analyzing collisions and searching for new particles. With the upcoming high-luminosity upgrade, the LHC will collect 10 times more data, enhancing its ability to make new discoveries. Machine learning and advanced mathematical techniques are increasingly being used to manage and analyze this data. These tools help improve particle detection and search for patterns that could indicate new physics. The LHC has already transformed our understanding of the universe, but much more remains to be discovered. With continued advancements in technology and data analysis, the LHC will likely uncover even more secrets of the cosmos, potentially leading to groundbreaking new theories and discoveries in physics. The field of machine learning holds thrilling prospects, particularly in the realm of a novel search technique known as anomaly detection. Unlike traditional approaches exemplified by the discovery of the Higgs boson, where scientists had a clear target in mind, anomaly detection aims to uncover unknowns. According to researchers like Duote, this method does not require the algorithm to search for predefined phenomena. Instead, researchers feed the algorithm with vast amounts of data and instruct it to compress this information as succinctly as possible, effectively highlighting the anomalies without preconceived biases. Anomaly detection is still in its infancy and has yet to reveal any groundbreaking insights in physics. Nevertheless, proponents are enthusiastic about its application to data from the upcoming High-Luminosity Large Hadron Collider, LHC. This approach is notably model-agnostic, meaning it does not rely on specific theoretical frameworks. Its goal is to identify anything that significantly deviates from the norm, thereby potentially uncovering new physics without the limitations of existing models. However, this innovative method has its critics. Some theorists express concerns that anomaly detection might result in numerous false positives, transient data fluctuations, such as the 2 sigma bumps, that disappear upon further scrutiny. Corin worries that the lack of a targeted approach might lead to an abundance of these false alarms. Knockman, who has faced resistance for advocating this method, recounted an instance where a senior physicist dismissed the approach, arguing that without a specific model, it strays from the realm of traditional physics. In the pursuit of precision, particle physicists face challenges with the current proton-proton collisions. Protons are composite particles, comprising quarks, and their collisions resemble a chaotic subatomic skirmish. Conversely, collisions involving elementary particles like electrons and positrons are much cleaner, akin to well-ordered interactions on a pool table. An electron-positron collider, envisioned as a Higgs factory, would facilitate the production of Higgs bosons with unparalleled clarity. Yet, no existing collider possesses the requisite energy for probing the Higgs boson effectively. The Future Circular Collider, FCC, is one proposed solution, envisaging an underground ring spanning 55 miles, 3 times the size of the current LHC in Switzerland. This ambitious project, estimated to cost tens of billions of dollars, may not be realized until around 2050. Meanwhile, nearer-term proposals for electron-positron colliders in China and Japan face geopolitical and budgetary hurdles. The aspiration to achieve higher energy levels remains a significant challenge due to the low mass of electrons. CERN's long-term vision includes utilizing the FCC tunnel for proton collisions at energies 8 times greater than the LHC, projected to occur about 50 years from now. The question of achieving higher energies more rapidly has led to innovative proposals, including those by the Particle Physics Project Prioritization Panel, P5. In December, P5 suggested a bold initiative to develop technology for muon colliders. Muons, despite their fleeting existence of just 2.2 microseconds, offer the promise of high-energy, clean collisions. Over the past decade, researchers have made significant progress in managing the energy from decaying muons during acceleration. A muon collider, potentially constructed within a 10-mile circumference, could become operational as early as 2045. Femilab, located near Chicago, is a potential site for this venture. Despite the technical, financial, and political challenges, the endorsement of muon collider research and development signals a hopeful future for younger physicists, opening new frontiers in particle physics. Simultaneously, physicists at the LHC are making strides toward explaining the predominance of matter over antimatter in our universe. According to the standard model of physics, the Big Bang should have produced equal amounts of matter and antimatter. If this were the case, the mutual annihilation of these particles would have resulted in a universe filled only with radiation. The existing disparity suggests a fundamental asymmetry known as charge conjugation parity, CP violation. In 2013, scientists observed CP violation in the decay of beauty mesons and strange beauty mesons, where matter and antimatter variants exhibited different decay behaviors. Recent findings from the LHCb experiment have precisely measured key parameters in the CP-violating decay of these mesons. This enhanced understanding helps constrain theoretical models attempting to explain the matter-antimatter imbalance, a crucial element in elucidating why our universe is dominated by matter. These advancements highlight the dynamic and multifaceted nature of modern particle physics. Whether through the innovative application of machine learning in anomaly detection, the pursuit of cleaner collision environments, the development of muon colliders, or the quest to solve the matter-antimatter conundrum, physicists are pushing the boundaries of our understanding. As these endeavors progress, they promise to unveil new insights into the fundamental workings of our universe. Thank you for joining us today. If you enjoyed this episode, please give us a thumbs up and subscribe to our channel. Don't forget to hit the notification bell to stay updated on future content. We welcome your thoughts in the comments section. Your support drives us to continue delivering high-quality content and to keep improving. Thanks for watching, and we'll see you next time.